Okay, in this lesson we're going to be looking at Unit 6, Chapter 6, Trigonometric Identities. We're looking at Reciprocal, Quotient, and Pythagorean Identities, Part 1. We're going to look specifically at what is an identity. Okay, first of all, we're dealing with Section 6.1, and the main focus for this lesson is going to be on explaining the difference between a trigonometric identity and a trigonometric equation, and verifying a trigonometric identity numerically and graphically using technology. Okay, first of all, what is an identity? Well, here's the definition of an identity. A trigonometric identity is a trigonometric equation that is true for all permissible values of the variable in the expression on both sides of the equation. As we proceed through this lesson, we'll get a better understanding of what that statement is actually saying. Some examples of identities that you've already seen are the reciprocal ratios, also known as the reciprocal identities. Cosecant x equals 1 over sine x, secant x equals 1 over cosine x, and cotan x equals 1 over tan x. These are called the reciprocal identities. A couple of quotient identities you've seen as well. Tan x equals sine x over cosine x, and cotan x equals cosine x over sine x. As an example, cosecant x equals 1 over sine x for all values of x, except values of x where sine x equals 0. And the reason being, again, because we can't have a denominator equal to 0. So this identity is true for all other values of x, except those values of x where sine x equals 0. In other words, when x is equal to pi n, where n is none of I. So if we go back to our definition here, a trigonometric equation that is true for all permissible values of the variable on both sides of the equation. So again, this is true for all permissible values on both sides of the equation, except, of course, these values of x where sine x equals 0, but again, these are non-permissible values. So it is true for all permissible values. How does this differ from a trigonometric equation? Well, an identity is true for all permissible values, whereas an equation is only true for a smaller subset of the permissible values. As an example of that, let's take the equation 5 sine theta subtract 1 equals 4 sine theta. If we look at the graph of both of these equations, I've graphed both of them. The red one is the graph of y equals 4 sine x, so I've graphed the right side of the equation. And I've also graphed the left side of the equation, y equals 5 sine x subtract 1. And you can see that this equation is only true for these values of x. Negative 3 pi over 2, pi over 2, and so on and so on. The equation is only true for values of x, or theta in this case, where theta is equal to pi over 2 plus 2 pi n. So as you can see, this is an equation, not an identity, because it's only true for a subset of the permissible values. How can you tell if something is an identity? Well, one thing you can do is draw the graphs. If the graphs of both sides of the equation are identical, then it is an identity. Or, if you can find a permissible value that does not satisfy the equation, then it is not an identity. So if you can find one permissible value that does not satisfy the equation, then it's not an identity. So if we look at this equation here, sine x equals cosine x times tan x, is this an identity? Well, I've graphed both equations for you. I've graphed y equals sine x, and I've graphed y equals cosine x times tan x. Is this an identity? If we look at both graphs, we see that both graphs are identical. So we say that yes, this is an identity. Now there are non-permissible values in this equation. And it's going to be where tan x is equal to 0, which of course refers to, sorry, not tan x equals 0, but rather where sine over cosine is equal to 0. In other words, where cosine x equals 0. So there are going to be non-permissible values. It just means that there are holes in the graph of this function here, that's all. But if we look at the two graphs, they are identical, so we can say that it is an identity. We'll get more into non-permissible values in the next lesson. Is this an identity? Sine x equals the square root of 1 minus cosine squared x. I've again graphed both equations for you. Here in red is the right side of the equation, and in blue is the left side of the equation. Now the actual graph in blue I'm going to highlight it for you because it's a little difficult to see. But the blue graph actually does this. This is the graph of y equals sine x, as you know. So when we compare the blue graph, or in this case not a highlighted graph, with the red graph, the question is this an identity? Is it true for all permissible values of x? And the answer is no. If you look at negative pi over 2, for example, negative pi over 2 is a permissible value. But is the equation true for this value of x? No, it isn't. When x is equal to pi over 2, the sine of x is 1. When x is equal to pi over 2, the square root of 1 minus cosine squared x is actually negative 1. Actually, that's just the reverse, sorry, because this is the graph of sine x here, sorry. So when x is equal to pi over 2, sine x is negative 1, sorry, whereas when x is equal to pi over 2, this side of the equation, which is the red graph, is equal to positive 1. But again, notice that it's not true for both sides of the equation. So although this is a permissible value, it's not true for both sides of the equation. As a result, this is not an identity for that reason. And again, if you look at your definition over here, a trigonometric equation that is true for all permissible values in the expression on both sides of the equation. So it has to be true for all permissible values. In this case, it isn't. I just found a permissible value that this equation is not true for on both sides. We're going to have a look at taking an example now. We're going to try and verify that an equation is true for a specific value of x. So, as an example, cotan squared x plus 1 equals cosecant squared x. Let's verify that this equation is true for this particular value of x. So all we need to do is simply find the cotan squared of pi over 6 plus 1, and we're trying to show that that's equal to cosecant squared of pi over 6. Okay, so in order to do this, we're going to use our unit circle. So let me draw a unit circle here for you. There we go. And we're looking at pi over 6. Pi over 6, as you should know now, is a reference angle of 30 degrees. Pi over 6. Reference angle of 30 degrees. The coordinates of the point associated with that reference angle, you should know as well, is equal to root 3 over 2 and 1/2. So I'm trying to find the cotangent of pi over 6. Cotangent is equal to cosine over sine. So the cotan of pi over 6 is equal to the cosine of pi over 6 divided by the sine of pi over 6. The cosine of pi over 6 is root 3 over 2, divided by the sine of pi over 6, which is 1 over 2. If I divide those two, I'll get an answer of root 3. The cotan of pi over 6 is root 3. Of course, this is cotan squared of pi over 6, which is really this root of 3 squared plus 1. The root of 3 squared is 3 plus 1, which is 4. So I can see that the left side of my equation is 4. I need to show that the right-hand side of the equation is also 4. So now I need to find the cosecant of pi over 6. Well, the cosecant of pi over 6 is equal to 1 over the sine of pi over 6, which is simply the reciprocal of sine. There's the sine of pi over 6. The reciprocal of 1 over 2 is 2. Of course, it's cosecant squared, so I got to square the 2 to get 4, and you can see that the left-hand side does equal the right-hand side. I've proven that this equation is true for that one value of x, pi over 6. Does this prove that the equation is an identity? And the answer is no. I've only proven that it's true for a specific value. That's certainly not enough to prove that it's an identity. There may be other values where this equation is not true. It turns out that this equation actually is true. We don't know that unless we were to graph both sides of the equation and show that both sides of the equation, when graphed, are the same. But from looking at it, we can't really tell at this point, based on the information that we did earlier there. By just simply showing the left-hand side equals the right-hand side doesn't do it. Let's have a look at another example here. Use the graph shown to determine which statement is correct regarding the equation 3 cosine x subtract 1 equals 3 times the square root of 1 minus sine squared x subtract 1. If you look over here on your right-hand side, I've graphed both again. Here's the graph in red of the right side of the equation, and in blue is the left side of the equation. And again, the graph in blue, a little difficult to see, but it's actually all of this graph here I'm about to highlight for you. You probably won't see that until I lift my pen. But here's the graph of 3 cosine x subtract 1, right there. Now then, which is true? The equation is an identity, A. B, the equation is an equation but not an identity. Or C, it is both an equation and an identity. Or D, the equation has non-permissible values. The correct answer, hopefully you'll agree, is that it is an equation, but it is not an identity. It is not an identity because there are permissible values of x that have 2 different values for y. As an example, when x is negative pi, I get y equals 2 on the graph for the right side of the equation, whereas I get negative 4 on the graph for the left side of the equation. So because there are values of x that are permissible values of x, and we don't get the same answer for them, then we immediately say that this is an equation, but it's not an identity. Of course, there are values of x, there are permissible values of x where this is true for both. Like there, for example, when x is 0, both equations will give an answer of 2. So there are values of x where both equations are true, but they're not true for all values of x. And as long as I can find one, then we can say it's not an identity. Example 3. When x equals 45 degrees is plugged into this equation here, secant x over tan x plus cotan x equals cosine x, both sides of the equation equal root 2 over 2. So if I plug in 45 degrees for x, I will get root 2 over 2 equals root 2 over 2. Which statement is true? The equation must be an identity since the left side equals the right side. To truly tell if the equation is an identity, we must graph both sides of the equation. The equation is not an identity since there are non-permissible values for tan x and cotan x. And since the equation is true for 45, it must be true for all values of x. Let's look at these a little closer. The equation must be an identity since the left side equals the right side. This only proves that it's true for that one value of x. It doesn't prove that it's an identity. An identity is true for all permissible values of x, so it can't be A. Let's move then to C. The equation is not an identity since there are non-permissible values of x. That doesn't mean that it's not an identity. There will be non-permissible values of x, but remember it's only the permissible values of x that we're concerned with to determine whether it's an identity. And since the equation is true for 45 degrees, it must be true for all. Definitely not. There may be values of x where this is not true. To really tell if the equation is an identity, we need to graph both sides of the equation and see if both sides of the equation give the exact same graph, and if they do, then this would be an identity. So the only correct answer here is B. Summary here of key ideas. A trigonometric identity is an equation involving trigonometric functions that is true for all permissible values of the variable. You can verify trigonometric identities numerically by substituting specific values in for the variable, which we did, graphically, which we saw using technology. And we can verify that 2 sides of an equation are equal for given values is not sufficient. Verifying that 2 sides of an equation are equal for given values is not sufficient to conclude that the equation is an identity. Just because it's true for a particular value does not verify that the equation is an identity. And that ends this lesson.